For the absolute maximum and minimum worksheet, I'm going to start with some quick review of interval notation. Close bracket, a comma b close bracket. This is a closed interval, means we're including the two endpoints. So we're looking for all x such that x is greater than or equal to a and x is less than or equal to b. Here, open interval means that we're looking for all x such that x is greater than a and x is less than b. Note there's no equals here. We're not including the endpoints. And then this last one, just to make sure that we're clear about open and closed intervals, a side is an open interval, the b side is a closed interval. So we're looking here for all x that are greater than a, not including a, and all x that are less than or equal to b. We're including b. Right? So example 1. We're looking at this function over here, some sinusoidal, modified sinusoidal function. It has relative maximum. Looks as if there are 3 relative maximum. There's one here, there's one here, there's one here. So the relative maximum are at somewhere in the 1-ish vicinity, where x is 1, where x is 5, and where x is 9. The absolute, this is the key word for these notes, absolute. The absolute maximum is right up here. That's the largest of the maximum of the maximums. And it's where x is 1-ish, somewhere in the 1 vicinity. And the value, you come over and look on the y-axis, the value of this absolute maximum is 6. This function has 2 places where it has an absolute minimum. If we're just doing this by inspection, it looks like right here and right there are both equally minimum. So the absolute minimum occurs both at 7 and 11, and the value for that looks to be 3. Right. Definition for you down here. Definition of an absolute maximum. The absolute maximum, 2 parts to the definition, and this definition here is a mathematical definition. So we have some function f such that the value of f of x is always less than or equal to m on the interval that we're interested in, and somewhere on that interval f of x is exactly equal to m, and then that makes m the absolute maximum. Right? So in less mathematical terminology, the absolute maximum is the y value. It's the number that's achieved. We hit that number, but we never go over it. And then obviously there's a similar definition for an absolute minimum. Right? Okay, so some examples here, identifying maximums and minimums, and there's some places here where we have to be very careful with, have to be very precise. So let's start with simple graph y is equal to x squared, which looks like this. And if we're looking for the minimum is easy. The minimum is at 0. The maximum, well, the maximum is up here, it just keeps going. We don't know exactly what it is. We know that it's infinity. But if we are asked to give the maximum value, our answer has to be, well, I don't know exactly what the value is. I do know that it's infinitely big. And so technically, we define the maximum value of this function as does not exist. And it doesn't exist because it's infinity. Problem B, we're looking here now on the closed interval. So we're looking at from 0 to 3. So we're looking at just say that piece that is right there, that the x starts at 0 and ends at 3. So on that interval, the minimum is, again, 0. The maximum, because we've defined this as a closed interval, our maximum is right here. And the maximum is 9. For C here, notice the only change here is that it's closed on the left side, closed at 0, so that means our minimum continues to be 0. But now on the right side, it's an open. We have an open interval, so it's all of the values up to 3, but not including 3. And if we think about this for just a second, let me get my cursor in the right place. So we can make sort of a little table of values here. If x were really close to 3, say 2.9, then the y value would be 8.99. If we got a little bit closer to 3, say 2.99, the y value would be 8.999. Right, so our y values are getting closer and closer to 9, but they never get to 9. And again, if we are asked what is the maximum value, we can't give an exact answer. We know that the maximum value is going to be really close to 9. We don't know how close to 9 it's going to be. So technically, we have to say that the maximum value does not exist because this is an open interval. All right, D. If we look at this graph, again, a very straightforward graph. Oops, didn't want that. I want a line. Try again. So we just simply have a horizontal line with crossing the y-axis at 7, and we're looking at this open interval on the 0 side and closed interval on the 3 side. So we have open, it doesn't look like an open interval. Let's try that again. So let's do it this way. We're going to erase this part and note that that's open there, and that when we come out to 3, this is closed here. Right, so that's 3. So we're just looking at that piece that goes from 0 to 3. Now, on the 0 side, when we're looking at the minimum, we're never going to get to 0, but we're going to get really close. And if we were, again, to make a table of values for this, x and y, if we were at 0.1, well, we would be at 7. If we were at 0.01, even closer to 0, we would still be at 7. And if we were at 0.001, again be at 7. So here, in this case, we can say what the minimum value is. We don't know exactly where it's going to be. We know it's going to be really close to 0, but whatever it is, it's going to be 7. And then obviously over on the right side where we can define, we are including the endpoint, we know that the maximum is going to be 7. All right. E, this graph looks like this. Asymptotic up to the y-axis, asymptotic out to the x-axis, and then for negative values of x, it's looking like this. Again, asymptotic down to negative, asymptotic out to 0, to the y-axis, asymptotic out to the x-axis. And here we're looking for it between 1 and infinity. So we are starting at 1, closed interval at 1, and then we're going out to infinity. Timer's on. Let's see if I can finish these notes before my computer runs out of power. So the maximum is clearly defined as 1, and the minimum is going to get really, really close to 0, but not going to equal 0, and we don't know exactly how close to 0 it's going to get. So then technically, precisely, we have to define the minimum as does not exist. Last graph here, by doing x squared, looks like this. Now, if we're defining our interval from 0 out to infinity, now we're looking at this here. We get infinitely close to the y-axis. We never get there. So the max is going to, again, does not exist. We know that it's going to be infinity, but to be precise, we have to say that the maximum value does not exist, and also the same thing for the minimum value. The minimum value does not exist. All right, moving on to page 2 of our notes. So here we're defining the extreme value theorem. And what the extreme value theorem says is that if you have a closed interval between a and b, and you have a continuous function, the functions we were talking about on the first page were not all continuous functions. But if we have a continuous function on this closed interval ab, so that means that we start at a and we're going to do something continuous, and we get ourselves to b. And there are obviously lots of different ways that that can happen. But what the extreme value theorem says is that, we'll write this out here. So the extreme value theorem says that a continuous function on a closed interval will always have, will always have an absolute max or min. Right, so if you're going from A to B, you're going to have a maximum value, you're going to have a minimum value. You have no choice. You can't get away from that. And the more important part is that those maximum values will occur at a critical point, or, and this is the important part, or it could be that they happen at an endpoint. Again, this right here is, oops, that didn't work. I missed. Let's try this. That is the critical part of the extreme value theorem, is that the maximum or minimum is going to occur somewhere within the interval or at the endpoints. Right? So let's look at this last example, and then we'll be done with the notes. So we're looking for the maximum and minimum values. You're looking for maximum and minimum. You're going to use the first derivative test. So we'll find the first derivative of this. So the first derivative of this polynomial, and just as a note, this here is a polynomial. Polynomials are defined as poly meaning many, nomial terms, so we have many terms, and each term is comprised of a coefficient, a variable, and a positive integer exponent. So if we have all positive integer exponents, it's a polynomial. Knowing that it's a polynomial means that it's continuous. So we know that this function here is continuous, so it meets the condition of the mean value theorem, and then the conclusion of the mean value theorem is that somewhere in this interval or at the endpoints are the maximum, absolute maximum, and the absolute minimum. Right? And to find those, we use the first derivative test, which is what I'm doing right here. I'm going to take the derivative of our function, which is going to be 3x squared minus 12. And now, since I'm looking for the critical points, I want to factor this. This is going to be 3 times x minus 2 times x plus 2. And now I'm going to do a number line analysis. So I'm going to do it this way. I'm interested in all of the values, including up to 5, and then the lower end is at -3, and I have 2 critical points here. One of them is at -2, the other one is at +2. And so now what I need to do is figure out where first in here in this chunk is the first derivative increasing or is it decreasing. So if you plug in a -2.5 in here, you'll find that this term here is going to end up being negative. Not term, this factor here is going to be negative. This factor here will also be negative. So that means that in that interval we are increasing. Our function is increasing. Its slope is positive. In this interval, if we were to plug in something in this interval, say +1, this factor would end up being negative. This factor would end up being positive. So that means that the derivative in this interval here is negative. So we are decreasing. And then over here in this last interval, if we plug in, say, 3 minus 2 positive, 3 plus 2 positive. So again, we're back to positive. Right? So what we have is we have a function that is increasing up to 2, increasing until x gets to be -2. It's decreasing till x gets to be +2, and then it's increasing again out to 5. And we're looking for the absolute max and the absolute min. So we look for those. If we're looking for the min, well, the min can be either here, or here. We got those three places that we're looking for the min. And if we're looking for the max, so the max can be either here, here, or here. These three, there we are. My program is catching up with my words. Sorry about that. So these three places. So what I'm going to do is quickly evaluate my function at -3, at -2, at 2, and 5, and then I'll be able to figure out where the absolute min and absolute max are. So at -3, the function has a value of 12. At -2, the function has a value of 19. At +2, the function has a value of -13. And at 5, the function has a value